Greetings everyone! In this video, me and my partner will share some interesting information and a demonstration of using the spectrophotometer. But before that, let's get introduced briefly to the spectrophotometer. A spectrophotometer is an analytical instrument used to measure the amount of light absorbed or transmitted by a substance at specific wavelength. So, how does this machine work? In the spectrophotometer, a prism or grating is used to split the incident beam into different wavelengths. By suitable mechanism, wave of specific wavelength can be manipulated to fall on the test solution. The range of the wavelength of the incident light can be as low as 1 to 2 nanometer. The spectrophotometer is useful for measuring the absorption spectrum of a compound, that is, the absorption of light by a solution at each wavelength. Let's dive into the principle of the spectrophotometry. The first principle is the absorption of light. Spectrophotometry is based on the idea that molecules absorb specific wavelength of light. When light passes through a sample, some wavelengths are absorbed by the molecule, while the rest are transmitted. This absorption pattern forms the basis for analyzing substance. The second principle is the Beer-Lambert law. This law establishes a relationship between absorbance and the properties of the sample. Essentially, this law allows us to determine the concentration of a substance by measuring how much light it absorbs. The third principle involves the spectral characteristic of substance. Every substance has unique absorption spectrum, which helps identify and characterize molecules. These patterns of absorbance are specific to each molecule, making it easier to analyze and differentiate substance. The fourth principle focuses on the use of monochromatic light. A spectrophotometer uses a monochromator to isolate a specific wavelength of light. This ensures that the measurements are accurate, because the chosen wavelength corresponds to the maximum absorbance of the target substance. The fifth principle highlights the concept of transmittance and absorbance. Transmittance is the fraction of light that passes through the sample, while absorbance measures the amount of light absorbed by the sample. The final principle explains the measurement component of a spectrophotometer. A spectrophotometer consists of four main parts. First, there is a light source that provides the illumination. Second, there is a monochromator that selects a specific wavelength of light. Third, there is a sample holder where the sample is placed for analysis. Finally, there is a detector that measures the intensity of light before and after it passes through the sample.
This is blank and this is sample containing. Let's take a look on how I prepare the sample. Prepare the sample by dissolving it in a suitable solvent. Ensure the sample is free from particles by filtering or centrifuging if necessary. Fill a cuvette with the blank solution before place it in the spectrophotometer. Turn on the spectrophotometer and allow it to warm up for a stable light sources. Calibrate the instrument using a blank solution. Measure and set the blank's absorbance to 0 to account for any absorbance due to the solvent or cuvette. Next, transfer the sample to a clean cuvette, ensuring the path length is consistent. Insert the sample containing cuvette into the spectrophotometer. Measure and record the absorbance or transmittance. Set the desired wavelength corresponding to the analyte's maximum absorbance. What is the spectrophotometry used for? First, quantitative analysis of biomolecules used to determine the concentration of nucleic acid and protein by measuring absorbance at specific wavelength. Second, clinical diagnostic, measurement of blood, glucose, cholesterol, hemoglobin, and enzymatic activity. For example, enzymatic glucose assays in diabetic monitoring. Third, environmental monitoring, detection of pollution such as heavy metals, nitrates, or phosphate in water sample. For example, monitoring nitrate levels in agricultural runoff. Fourth, pharmaceutical analysis, quantification of active pharmaceutical ingredients in drug. For example, assessing the concentration of paracetamol in tablets. 5. Food and beverage testing, determination of food colorants, antioxidants, and contaminants. Example, measuring the concentration of vitamin C in fruit juice.
Of all machineries we have in our lab, why do we choose spectrophotometer? Here are the advantages of the spectrophotometer. Firstly, it has high sensitivity. Spectrophotometer is capable to detect low concentration of analyte, making it ideal for trace analysis in biological and environmental sample. Second, it has quantitative and qualitative analysis. Spectrophotometer allow determination of both quantitative and qualitative measure. Quantitative measure is the concentration of substance, while qualitative measure is the identification of compound based on their unique absorption spectra. Third, it has wide range of application. Spectrophotometer is applicable in various fields such as biochemistry, pharmaceutical, environmental monitor, and food science. Fourth, spectrophotometer use non-destructive method. Spectrophotometer does not destroy the sample during measurement and allow further analysis if required. Fifth, it has rapid and efficient result. Spectrophotometer provide quick result with minimal sample preparation. 6. Spectrophotometer is cost-effective. Spectrophotometer are generally affordable compared to other analytical instruments and have low operational cost. Last and most importantly, spectrophotometer has a reliable accuracy.
The limitation of spectrophotometry. First, limited specificity. Spectrophotometry may not differentiate between compounds with overlapping absorption spectra. Second, interference from impurities. The presence of contaminants or turbidity can affect absorbance reading, leading to inaccurate results. Third, requirement for transparent samples. Sample must be free of particle or cloudiness to avoid scattering of light. Fourth, dependency on calibration. Accurate measurements require proper calibration with reliable standard, which can be time-consuming. 5. Restricted to absorbing molecules. Non-absorbing compound cannot be analyzed without prior chemical modification or derivatization.
In this part of presentation, we will discuss some real-world application of spectrophotometry. Firstly, spectrophotometry plays a critical role in biochemistry and molecular biology. It is commonly used to quantify DNA and RNA by measuring absorbance at 260 nanometer. The 260/280 nanometer ratio provides insight into sample purity with a ratio of approximately 1.8 for pure DNA and 2.0 for pure RNA. A 2022 study by Nguyen and his team demonstrated the use of spectrophotometer to evaluate DNA integrity in samples extracted from various tissue types for genetic study. The second application is in the pharmaceutical industry. Spectrophotometry helps quantify active ingredient in medication. For instance, paracetamol absorbs strongly at 257 nanometer, making it possible to measure its concentration accurately in over-the-counter formulation. A quality control study conducted by Kumar and his team in 2020 used spectrophotometer to assess the purity and the concentration of paracetamol in 10 different drug brands. Next is environmental monitoring, where spectrophotometry is essential for detecting pollutant. A common example is the detection of nitrate in water sample. A diazotization reaction produces a colored compound that absorbs light at 543 nanometer, allowing for the quantification of nitrate level. In a 2019 study by Chen and his team, spectrophotometry was used to monitor nitrate level in agricultural runoff, helping to identify areas with excessive fertilizer use. In conclusion, spectrophotometry is an incredibly versatile tool with application ranging from healthcare and pharmaceutical to environmental science, food analysis, and molecular biology. Its precision and reliability make it indispensable in scientific research and practical application. I think that is all from us. Thank you.